Trigonometry 6.1, angles and their measure continued. So we just did arc length. And how do we figure out arc length? We had S equals R times the angle, making sure this part is in radians. So how do we figure out the sector area? So again, we've got a pizza, and we'll divide it into 8 pieces. So it's the part with the cheese, assuming the cheese runs up and hits this infinitely small crust. So it's 45 degrees. A lot of people say, oh, just scale it. It's out of 360, and I'm going to put my 360 over here for a reason. No, I'm not. I'll just rewrite it. Times pi r squared. Piece of cake. Well, we'd like to do things in radians, so how about 45 times pi over 180, and I've broken this into 180 times 2. So there I just did this part, times 1/2 times r squared, saying this is the angle in radians. So this is what happens when you get to adult, for lack of a better way to put it, trigonometry. Everything's in radians. So the area is 1/2 theta r squared. This is in radians. So, example. How much area in a 40-degree sector of a circle with a diameter of 12 inches? I don't know if I mentioned this last time. I like to do this diameter trick because it's on the ACT and it really messes with people. Whenever I see the word diameter, my brain jumps and says, whoa, 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 right radius equals 6 inches. It's just a trick teachers use to nail you. So area of the sector, and I'm not going to write sector like that again. I just did it once. 1/2 r squared times radians. All right, I'm going to, again, leave pi in the answer because why not? It's just so much easier. Blast out the rest of this, and I get a possibly nice number. Yeah, whatever. 4 pi. Which makes sense. Cancel 0, 18, 36, 2. Yep, 4 pi. So that's not that bad. Now things get bad. Lots of things are rotating. Let's just say a carousel. And you're on a horse. I know how bad the horse is. You don't have to tell me. And your friend's on a horse that's a little bit closer to the middle. Whatever. I'm not going to try and draw the people. This one's going around here, and this one's going around here. So somebody who is not a physicist might say, who's going faster, horse A or horse B? And to which I would say they're both rotating at the same speed. But one of them's moving much faster. They both make a cycle every, 20 seconds. All right? But A has a higher linear velocity. And B has a lower linear velocity. What does that mean? That means if the bolts broke on the bottom of the little horse they're sitting on, and it went shooting off into space, horse A would be moving much faster. It's out on the edge of the circle. This is very similar to if you're in a car and it takes a hard turn. If you're sitting on the side closer to the inside of the turn, you feel a pull, you want to get shot out, but not that big a deal. If you're sitting on the far side, you get slammed into the window if somebody really jerks on the steering wheel. So this is a very challenging concept for people to understand. Linear velocity, I run down the field at 100 miles an hour. I am running at 100 miles an hour. Angular velocity is how many times we're rotating. and they are different. You have to get that down. This is a Greek letter. It's omega, lowercase omega. A lot of people draw it as a W. Try and get the tops to close in a little, if you can. It is how many radians you go in a unit of time, most often seconds, minutes, or hours. I'm not sure what else there is. I suppose we could do years. So, angular velocity of a wheel rotating 3 revolutions every second. 3 revs per second. One revolution has 2 pi radians. Multiply it out, and we will get 6 pi radians per second. This is where radians is going to bother you, so just get used to it. It's this magical unit that vanishes when I multiply it to get linear. Right? The wheel has a diameter, oops, I'm being a jerk again, r equals 8 inches. How fast is that car going? Well, we just said omega 6 pi radians per second. The velocity, linear speed, is the radius that we're traveling at. So the further from the center, the faster we're going, meaning, yeah, it doesn't matter what order we put it in. What do I usually do? I usually do RW, I guess. R omega, I should say. If the radius is big and we're rotating at the same rate, if you ever see one of those skating lines, people in the middle are barely moving in a nice easy circle. The person at the end of the skating line is whipping along. So you would say the velocity is 6 pi radians per second times 8 inches. 48 pi inches per second. Why don't we multiply out the pi? Because I don't have to. Until I have to, I'm not going to. Somebody wants to know what I'm doing, miles per hour, I'm going to multiply out the pi because then it's going to mean something. Hey, we're riding our bike at 750 miles an hour. Oh, we probably screwed up. We're riding our bike at 12 miles an hour. All right, that sounds reasonable. But I don't care right now. Until I need to put it into something that I can compare to, I leave the pi in until I have to. It's not a big deal. What happened to the radians? Where'd they go? Well, that's one of the magical properties of radians. When I multiply them against another unit, they vanish. Somebody else has given me a better definition than that. I didn't buy it. It just didn't work for me. So I just say they vanish. And, just so we're all clear, this causes confusion. This whole linear speed versus angular speed. I like to say angular velocity, and then I like to say linear speed. It doesn't matter. It just causes problems. So this is how you kill somebody. I mean, this is how you play with a rock. You put it on the end of a rope and you spin it around, and then you let go. And that's going to tell you how fast the rock will be flying based on the angular velocity. They're really whipping it around, 180 revolutions per minute. So when in doubt, I always find the angular velocity first. One revolution has 2 pi radians. (360 pi radians per minute). Okay, it's the end of a 2-foot rope, so I guess we can call that the radius. Although some of it would be in my hand, but we'll just go with 2 foot. So, V equals 360 pi radians per minute times 2 feet. 720. I'll put it down here because I need the space. Pi feet per minute. Well, how fast is that miles per hour? Oh boy, big question. I got to change things up here. There's 60 minutes in an hour. Cancel, cancel. There's 5,280 feet in a mile. Cancel, cancel. So take that 720 pi. And now I'm actually multiplying it out. I want to find out that this is reasonable. Divided by 5280. And that is 25 point. I'm always going to go 3 decimal places. You know what? I better go 3. That's what I did in my answer key. 25.704 miles per hour. Does that seem reasonable that you could whip a rock at that speed? I don't know if I'd call it reasonable, but you definitely can. That's why, it was a weapon in ancient times. It's extremely dangerous. You can really whip this thing and, crack somebody in the head. So I would pause and try this. What's the angular velocity of the wheels if we know the other way? So we know velocity is 30 miles per hour. Oops, I nearly forgot. I want to change that immediately. Radius equals 8 inches. 30 miles per hour. I got a lot of converting to do. Angular velocity. I'm not sure what to do with that. I'll figure that later. 1 mile. We'll go to minutes. I'm not going to go to seconds. 1 mile has 5,280 feet. 1 foot has 12 inches. 1 hour has 60 minutes. So miles, feet. Whoops. Yeah, feet. Hour. We'll end up with inches per minute. Make sure you know how to multiply this. It's tricky for some people. They kind of divide and do all that stuff sloppy. I like to do the whole top divided by the whole bottom. So you are going 31,680 inches per minute. Seems about right. And now let's go backwards. V equals omega times R. So omega equals V over R, 31680 inches per minute over 8 inches. And there we have it. The car has an angular velocity of 3,960 radians. Whoa, where'd radians come from? Remember, it's magic. And just canceled per minute. Very tricky stuff. Going to spend a whole day practicing this concept because people don't quite get it. So we'll tie it all together. But the good news is I got my happy mathing back, so that's all that really matters. Good luck.